And hello YouTube. In this video, we will be taking a short break from actual Rust coding, and we're going to be delving a little bit back into engineering. So, as you know, for those of you who studied chemical engineering, or in fact any engineering that deals with gases, you know that ideal gases, you cannot use that. For ideal gas equation, you cannot use this equation for every single situation. More often than not, you will need to use a more complicated equation of state, otherwise known as EOS. So this video, we want to talk a little bit more about real gases, and some of the references you can use include textbooks like Felder and Rousseau. These are classic chemical engineering textbooks, but I do want to share some of the useful resources I found online. These are Creative Commons, which you can use to study an equation of state a little bit better. All right, so this includes LibreTexts, and this is one of them. Okay, the other one is let's see, where did I leave it? Oh, great, I need to find it again. Yeah, the other one is this one. It's called taking a look at another look at the van der Waals equation of state almost 150 years later. It's open access, so that means you can use this article, you can see it for your own learnings. Yeah, and just yeah, the same rules apply, no plagiarism. You should still cite your articles and books. So this one for cubic equations of state. Well, you start from van der Waals equation of state. Yeah, this is a very useful article, so you should cite it. So I'm going to use the BibTeX and add this citation. So I'll copy this and I'll paste this into the Typst citations here. So if you're not sure how to cite your works in Typst or Typst, use I'll paste this link to the Typst or Typst docs. I like to call it Typst. I'm more used to it, even though maybe the authors want it pronounced as Typst, if I am not mistaken. If I am, just let me know. But yeah, here's how you can do citations. Have yeah, I'll just paste the link. You can go and take a look at it yourself. This is not the main focus of this video, so I'll not be doing that. I'm gonna paste this here. I'm gonna save this, and I'm going to copy this. Of course, you can use your own mouse to copy this. So this is the citation key, and what I'll do is that I'll paste it here. Okay, I'll paste it here. Oops, wrong one. Add. Okay. Right, so here's your citations. They will automatically show up here, so long as you do your bibliography right. This is the syntax right here. I'm not going to go through it, but yeah. So basically, real gases do not behave like ideal gas according to ideal gas law. We often use more complicated equations of state, right? So that's what we just discussed. I'm going to, oops, let me just do a combination. I don't know why there's a text wrapping here. I do not like text wrapping. Let me find out how to switch it off. I am not used to this. Okay, so after I'm supposed to use Alt-Z, and that should, yes, Alt-Z sort of switches off text wrapping. So that's a good tip for VS Code. I usually like to switch my text wrapping off so the Vim key bindings actually work a little bit better. Okay, that's the HJKL bindings. They work a little bit better when you don't have text wrap. Okay, so real gases do not behave according to the ideal gas law. Okay, so there's more you can actually read up. Okay, so besides this article, you can actually take a look at LibreTexts. Okay, LibreTexts. There are a few books you can use. One of them is this van der Waals equation under the physical chemistry section, thermodynamics and chemical equilibrium. But of course, we're more I'm doing more of a chemical engineering bent here, so I'll go to engineering. So I'll go to explore the libraries. That's today's LibreTexts in engineering. Okay, I'm actually going to the bookshelves. I'm going to look for chemical engineering, and there are a few books you can actually look at here. The most useful and insightful one is this one, called Phase Relations in Reservoir Engineering. Okay, it looks like it's done by Professor Michael from the Penn State. Looks like Dr. Michael or Professor Michael, I'm not sure. And I'm not sure how to pronounce the last name either. But as you can see here, these are Creative Commons license as long as you don't do commercial work with it. You see the license right here, so it is free. So, but just don't copy, just cite it and don't copy. So another one is Distillation Science right here, which you can do. You can see it's actually Creative Commons. Also looks like by Larry Coleman. And you can see this equation of state chapter right here. PDFs you can just download it as and how you like. I will leave the link to this chemical engineering bookshelf inside the description. So I'm just going to well, I'll have to do the citation here manually because I can't find it in Google Scholar. So let me fast forward this part. So here is that Distillation Science. You can actually download the PDF right here, but I'm not going to show that. You can just download it full and you go to the equation of state chapter. You'll be able to find some resources on that. And yes, of course, I want to look at the phase relations in reservoir engineering. This is very, very useful book. You can just download it online as well. Yep. And then yeah, I'll skip this part. I'll put in the citations, and yeah, we can like carry on from there. Okay, so let me quickly show you how the citation looks like. So I'll just show you my bibliography. Bibliography is right here. I cite the Coleman distillation one right here. Title is Distillation Science. Coleman, author is Larry Coleman. The year is 2023. Publisher is LibreTexts. Same for phase relations. Just put the author name. It was kind of done this year, and the publisher is also LibreTexts. So these are pretty good resources because I like. Thanks to them, it's free. You can go look at the phase relations yourself. I'm not going to show it in this because I'm not going to like just go through the textbook. But where you'll find the suitable things, the suitable pieces of information are cubic EOS of their behavior 1, 2, and 3. So that's chapters 9 through 11. It's a very good text for that. So without further ado, let me just start. Okay. Yeah, how do the equations of state look like? So if you actually follow the narrative in phase relations in reservoir engineering, or you do a quick online search, you'll notice that of course ideal gas is not suitable. Ideal gas equation is not suitable. So van der Waals actually was the first to sort of come up with a cubic equation of state. Okay, so the key assumptions in ideal gas are, number one, gas molecules or atoms take no space. Two, what's the second one? Or maybe let me use this. Yeah, let me use this. gas molecules and or atoms take no space, no attractive forces between gas molecules or atoms. Okay, you look online, you will be able to find some of these. Then maybe I'll just cite the phase relation textbook. Okay, so takes no space. So van der Waals actually, figured that, hey, maybe these assumptions are not true, right? These assumptions are not true. So we need a term to represent that the ideal gas sort of takes up space. So, or rather the gas takes up space. So this is the ideal gas equation. Now we need to change it. Okay, PV equals to nRT, right? So we want to say first, okay, I'm going to make this in the center. The gases take up space. Okay, this is the ideal gas equation. We're going to change it. So if these gases take up space, hold on. Yeah, if the gases take up space, then, well, if your temperature increase, right? If your temperature increase, your volume will increase at a constant pressure. So at a constant pressure, your volume will increase with temperature. But the total volume right here of the gas, the total volume of the gas is not just the space between the molecules, but the space taken up by the molecules themselves. Now, the space taken up by the molecules or atoms themselves, they are not going to be expanding with increasing temperature. So van der Waals actually added another term called B. You will see it online as B. All right. To denote that, hey, this volume is the only part of the volume that expands due to temperature increase at a constant pressure. That will be the part that is that's the volume between the gas molecules. So the volume between the gas molecules is this V minus V term. Okay, or if you want to take it in terms of the per mole, which is what you will normally find, you put a tilde right here. Okay, and then this will be sort of the volume taken by 1 mole of gas molecules. Okay, so it's a per mole basis, right? For per mole basis. All right, so that's how. So the B term here again, it accounts for the fact that gas molecules or atoms actually take up space. Now, of course, you will see that there are no forces, attractive. Okay, let me put attractive or repulsive. Okay, because if you push gas molecules or you push molecules close enough together, they will start to repel each other. Okay, so that this term you will actually find, right? You will actually find van der Waals actually putting another term right here. Okay, and it's actually as follows. Okay, A divided by, if I'm not wrong, tilde V square. Okay, A divided by tilde V square. So this term here is actually it represents the forces. Oh, it should be a plus, pardon me. So this term here is actually the forces, or rather it represents the forces between the molecules. Okay? Let's see if this is clearer. Yeah, this term here actually represents the forces between the molecules. Why is it a V square over there? Now, there's actually a little bit of a deeper reasoning to that. There's a lot of derivations. You probably have to read the original paper for it. Okay, but for now, conceptually, the force between the gas molecules or atoms, they are actually so-called accounted for using this term here. Okay, so that actually sort of simplifies. Oh, that's sort of how the van der Waals equations comes about. Okay, and so to make the ideal gas more realistic, then the Waals equation accounts for gas molecules, or rather, space between gas molecules or atoms and the forces between them. Okay, so I'm going to just cite this I cite Professor Michael, Dr. Michael with this, and the equation of state, the EOS. Okay, equation of state. EOS looks like, okay, and now I'm going to cite Felder. All right, good. That's autocomplete. Okay, so this is what the equation of states looks like. And what is A and B? A and B are just, let me type this out. A equals to 27 R squared TC squared. So TC is a critical temperature, and PC, as you'll find, you'll see shortly, PC, this is actually critical pressure. Okay, so this is A. This is the A term. Let me change the R to here. And just note that this R is the same R over here. This is the ideal gas, or the universal gas constant. Okay, universal gas constant. And what is B? Okay, B equals to RT divided by 8PC. Okay, so this is a critical temperature. Let me put a space between them. It should compound. Let me center the B as well. Okay, so this is the van der Waals equations. Okay, of course, van der Waals equations, if you actually look online, you will not see it being used very much today. But the way it's very useful because it helps our conceptual understanding of how a real gas equation should work. Okay, so if you actually read the phase relations in reservoir engineering, you will actually see that yeah, this is not the full picture. Okay, because gas molecules, they have different shapes and sizes. So for example, let me use GIMP. Yeah, for example, if you look at a gas molecule of helium, okay, helium is a noble gas. So I'm going to make a new one. Helium is a noble gas. It is just one He, and you're not going to find very much interesting things with it. So let's draw like a little bit of a circle here to say this is helium. Boy. Yeah, this is helium. All right. So then you have bigger gas molecules like nitrogen. Okay, and you just put a triple bond here, or maybe let's just put nitrogen. 1, 2, 3. Nitrogen. So it's a triple diatomic molecule, triple bonded. So you can see the shape here is sort of more elongated a little bit. Of course, it's actually rounded, but I'm not going to draw that over here. You have things like you have gas molecules such as propane. 1, 2, 3. Then you have the H here, you have the H here. So this is a propane gas. Let me pause this and then yeah, I'll fast forward the drawing. So you have gas molecules that are pretty so-called elongated. Okay, if you actually so-called go into your petrol engines or gasoline engines, depending on where you're from, you call it petrol or gasoline. You actually have petrol vapors or gasoline vapors. These are actually molecules of hexane, up all the way up to decene. So that's 10 carbons long. All these gas molecules will have different shapes, right? Gas molecules or vapor, I should say vapor, yeah. Vapor molecules, these have different shapes. So definitely all these will affect the forces between the molecules, right? All these will affect the forces between the molecules. So that is this term right here, this A over V square right here. So how do you actually account for this thing? How do you account for this problem? Okay, so you will see yet another improvement upon the van der Waals equation by Ridlich and Kwong and Soev, Ridlich and Kwong. So yeah, let me write what we've been talking about. Gas molecules, or rather gas or vapor molecules, are not uniformly shaped. Okay, the force between gas molecules depends on the shape. Okay, so these are the van der Waals forces. Same guy, I think. Van der Waals forces between gas molecules, they really depend on the shape. Okay, so what do you do? How do you actually account for the shape? Okay, so if you actually read the phase relations textbook, it'll give you a brief history. Okay, you'll see that Ridlich, Kwong, and Soev, Ridlich, Kwong. Okay, so it's commonly known as the SRK equation of state, helps account for this shape problem. Okay, so I'll just put there put this citation here. Right. So these equations actually help to deal with this problem right here. So what do you do? This is accounted for in, oops, what did I just do? Now must be a mouse thing, the touchpad. This is accounted for in the eccentricity factor. Okay. Eccentricity factor. So this is this eccentricity factor, the way you see it written in literature is denoted by omega. Okay, omega is the eccentricity factor. So the Soev, Ridlich, Kwong, the SRK equation of state, okay, is determined as follows. Yeah. Anyway, so just a note. The derivations for the van der Waals and the Soev, Ridlich, Kwong equation of state, or especially the Soev, Ridlich, Kwong equation of state, these are empirical equations. So A and B are not always, derived from first principles, but sometimes they are, part of it is actually fitted using experimental data. So it's very an empirical or semi-empirical. Okay, so this is the semi-empirical EOS. So semi-empirical accounts for, how do I say this? This is accounted for by the eccentricity factor in the Soev, Ridlich, Kwong equation of state, a semi-empirical equation of state. Okay, the SRK EOS or Soev, Ridlich, Kwong equation of state, that's how I pronounce it. I'm probably messing up the name. Is written as, I'm going to put Felder again, that's the citations, the equation of state is here. So okay, P, so okay, maybe I'll just copy this here. There's one sort of minor change in the equation form from let's say or rather two things of note. So yeah, this force between molecules, that depends on the shape factor. Okay, this greatly depends on the shape factor. This shape factor is accounted for in this A term right here. So the Soev-Redlich-Kwong equation of state will actually add another term, not just A, there's an alpha term as well. Okay, there's an alpha term here as well. So that's the first addition. What is alpha actually? Okay, so things will kind of get messy here, but don't worry too much. This is more of a empirical, semi-empirical way of doing things. So some of these things are data fitted. You don't need to know why things are so-called written like that. Okay, so let me just write this 1 minus square root of TR, and this whole thing is squared. So this is what the alpha term looks like. 1 plus m 1 minus TR squared. So what is m and what is TR? So m is actually the polynomial that deals with this eccentricity factor. So for it, let me do this. 485. All right, 48508. So don't worry about why the numbers are like that. Okay, 171 omega. And then one more term will be the square term, omega square. So this is a polynomial equation. It's just a data fit, if I'm not wrong. Okay, omega squared. So this is the term accounting for the molecule shape. Okay, so that is the first of the issues that this Soev-Redlich-Kwong solves. Then the second issue, of course, let me okay, we still have to do the reduced temperature. That's TR. Okay, so TR, you will see this a lot. TR is the reduced temperature, which is T. Okay, so this should be in Kelvin. Yeah, this is always in Kelvin for this thermodynamic equation of state. Do not forget it's in Kelvin, divided by Tc. Okay, so this is the reduced temperature. It's dimensionless. Remember, always have your equation of state temperatures in Kelvin or Rankine. As long as an absolute temperature scale, it should work. Okay, so that's the reduced temperature. So what this is saying is that yes, you're gonna have the shape factor, or we call this the eccentricity factor, because we have different shapes, molecules of different shape. That's going to affect the forces between the molecules. Not only that, of course, the temperature, how close it is to critical point, it will also affect the forces between the molecules. So that's why you have this reduced temperature thing here. Okay, so that's sort of how you calculate alpha. Okay, there's also another term that sort of gets what do you call that? Yeah, changed. That is this volume term right here. Yeah, so pardon, I think I made a mistake earlier. So anyway, yeah, there's one more. Soev-Redlich-Kwong equation of state actually makes one more modification to this volume that is over here. And earlier I said that I think this term here accounts for the attraction and repulsion force. So actually I had to refer back to the textbook. Okay, so what's that? I misspoke, or rather I forgot on hindsight. Yeah. So this A term actually accounts for attractive forces between molecules. This V term accounts for the volume occupied by the molecules. So this is the attractive force, this is the repulsive force. Okay, so so this attractive force between the molecules, it is a function of temperature and a function of shape. Okay, so of course, as your volume gets smaller and smaller, right? So if you have this A over V squared, right? If your volume gets smaller and smaller to 0, right, you cannot have your attractive forces go to infinity, so-called, right? You cannot have your attractive forces go to infinity. So if your volume goes smaller and smaller to 0, yeah, as your volume gets smaller and smaller to 0, you will sort of have more and more repulsive forces pushing back against the attractive forces. Okay, you'll find that the molecules actually, well, it makes sense that the attractive force doesn't go into infinity, but the attractive force also starts to dwindle, and then the molecules stop. The molecules sort of bang into each other, but okay, maybe the explanation is wrong, but this is how I think about it. Okay, when the volume between the gas molecules actually tends to 0, this equation is saying that the forces actually sort of go to infinity, which is not correct. So I guess one way to think about it is that, hey, the volume is not going to go to infinity. As your volume gets smaller and smaller, the actual volume of the molecules starts to sort of do a pushback. Okay, so this is sort of done here. So there's be some repulsive forces that actually come into play. So this is called the volume cofactor term. What I was saying was the sort of best way, or rather the way I knew how to sort of explain this away, right? But that's how I think about it. It might be wrong, I might need some rereading and concepts, but this is how my intuition is sort of taking this thing. So yeah, this term here actually says if your volume goes to 0, then or the volume between molecules, like volume between molecules goes to 0, then the attractive term is going to be sort of pushed back. You kind of really go to 0 all the way. You'll have the volume of the gas molecules themselves actually push, making sort of limiting how high this attractive force will be. I mean, if you think about it in electrostatic repulsion and all that sort of makes sense, but this is a hand wavy way I think of explaining this thing. So okay, right, so anyway, so far that's how this equation sort of, I conceptualize this SRK equation. All right, and of course that requires understanding of critical temperature and pressure, which I did not explain, so do go and read up on that. I'm not going to talk about it in this video. Supercritical fluids and so forth. I'm just going to focus on the SRK equation. So, all right, what terms were there in the SRK equation we already talked about? It is this alpha right here. So this is the alpha that accounts for the eccentricity factor, and and also the temperature of the molecules, because the temperature of the molecules actually affects the attractive forces between the molecules. So this is where this reduced temperature thing comes in. And of course, this A and B here, they are not going to be the same as the A and B over here. So this is actually modified, a modified form of A and B. Okay. So there are going to be numbers here, and just don't ask me why there are such numbers here. Okay, because it's probably an empirical correlation for all you know. But the R square TC square over PC term still remains the same. It's just that this coefficient at the front sort of changes. My guess is that this is a empirical correlation. Okay, this number here is probably empirical. So, and this divide by 8 thing right here will be taken out. Will be some decimal number that, again, not too sure why, probably is fitted to experimental data also. So this is the SRK equation of state. Okay, equation of state is as such. You will need to know the what do you call it? You will need to know what a critical gas is, what's a critical point, of course. But yeah, this is how I sort of think up the SRK equation of state. So this is a very much more general sort of equation of state that's being used today. Of course, there are others like the Ping-Robinson as well, which I'm not going to discuss now, but that one's more for oil and gas application. So I'll just stop the video here. We'll talk more next time about this. So cheerios, see you next time. Bye-bye.